In this lesson we're going to look at a few more trig equations. These are going to be more complicated than the ones we did in the previous lesson. Basically what we're going to have to do is we're going to have to use our identities to, a lot of times, rewrite equations so that they're in terms of a single trig function. You'll have ones where you have a cosine and a sine in it, or a cosine squared, or a sine squared, and you'll need to use the Pythagorean identity or even some double angle identities sometimes to rewrite in terms of a single trig function. So we're going to work through some examples here, and then we'll do some more in class. So here's our first example. I want to solve 1 plus sine of x equal to 2 cosine squared. We're going to solve it over one complete rotation around the unit circle, 0 to 2 pi. So if you look at this, I have a sine and I have a cosine squared. I've got to be able to rewrite this all in terms of one trig function. Well, it's pretty difficult to rewrite sine because I don't have a trig identity that lets me do that very easily. But I do have one for cosine squared. I can replace cosine squared using a Pythagorean identity, and that's equal to 1 minus sine squared. So that's what I'm going to do. Now my trig equation looks like this. 1 plus the sine of x is equal to 2, and then instead of cosine squared, I'm putting in 1 minus sine squared of x. We treat this like a second degree equation, and we get all of our terms on one side in standard form, and then take a look and see if we can factor it. So I have 1 plus sine of x. I'm going to distribute the 2, and then I'm going to add 2 sine squared of x to the other side, plus sine of x. I have a 1 minus a 2, so that's minus 1, and that's equal to 0. If I let x, or y, let's let y, be equal to the sine of x, I can make this look a little bit better. 2y squared plus y minus 1 is equal to 0. You break up the 2y squared as a 2y and a y, and a 1 and a 1. You put your signs in there so that you get a positive 2 and a negative 1. And that is factorable. That gives you your positive 1. So you have 2y minus 1 is equal to 0, and y plus 1 is equal to 0. Y ends up being 1/2, and y ends up being negative 1. But remember that it was originally sine of x. So you put your sine of x back in. Over that interval, the sine of x is 1/2 at 30 degrees, so that's pi over 6, and also 5 pi over 6 because it's positive in the second quadrant, but I only put 2 there because that's where it's positive, and I have a positive 1/2. For sine of x to be negative 1, there's only one place where sine of x is negative 1, and that's at 270 degrees, so that's 3 pi over 2. So those are your solutions. Here's our second example. In this one we have sine of 2x minus cosine of x is equal to 0. I don't have any squared terms here, so I can't use the Pythagorean identity, but I can do something with sine of 2x because the identity for sine of 2x is 2 sine of x cosine of x. And then that's minus cosine of x, and that's equal to 0. Now granted, this is not in terms of one function. However, this is factorable, and that's what I want. Since both terms contain a greatest common factor of cosine of x, I can factor that guy out, and I'm left with something solvable. So you can have two different functions if they are factors, because I'm still going to set each factor equal to 0 and solve each one individually. 2 sine of x minus 1 is equal to 0. So the sine of x is once again 1/2, and the cosine is 0. Cosine is 0 at 90 degrees and 270 degrees, so that's pi over 2 and 3 pi over 2. For sine to be 1/2, remember it's pi over 6 and 5 pi over 6. So those are our solutions. When we get to class, we're going to figure out how to use our calculator to check our work. So sometimes you don't have much to go by, and you'll have to square both sides to create an identity, because we can always use the Pythagorean identity if I have squared terms. So in this example, cosine of x plus 1 is equal to sine of x. There's nothing I can really do there. Even if I divided each thing by, let's say, cosine, I would still end up with two different functions, so I can't isolate it. What I would do here is I'm going to square each side. The left-hand side is a binomial. It ends up being cosine squared of x plus 2 cosine of x plus 1, and on the other side is sine squared of x. Since I have a cosine squared and a regular cosine, I want to rewrite sine squared in terms of cosine. Again, that's the Pythagorean identity. It's going to be 1 minus cosine squared. And now I have something I can solve. Cosine squared of x plus 2 cosine of x plus 1 is equal to 1 minus cosine squared of x. Putting this in standard form, my 1's are actually going to add to 0, so they're going to go away. And I end up with 2 cosine squared of x plus 2 cosine of x is equal to 0. I can divide away the 2 because he shows up in every place, so he goes away, and I can also factor out a cosine. So I end up with cosine of x is equal to cosine of x plus 1, or is not equal to, times cosine of x plus 1 is equal to 0. Setting each factor equal to 0, I have cosine of x is equal to 0, and then cosine of x plus 1 is equal to 0. In this case, I have pi over 2, because it's 90 degrees, and 3 pi over 2. Over here, I'm looking for values where cosine of x is equal to negative 1, and that's going to be at pi. Now, since I squared this thing, you have to check your answers, because I'm going to introduce, or I could possibly introduce, factors that aren't correct. So you got to check your solutions to see which ones work. And if you do that, pi over 2 is good, because pi over 2, the cosine of pi over 2 is positive 1, and that checks out here. But what doesn't check out is 3 pi over 2, so I can't use him. So my solutions in this case are only going to be pi over 2, and then if you try out pi also works. So you have to check your answers when you're squaring both sides. And finally, sometimes your answers are not going to be a special angle. In that case, you just have to use your calculator. If I want this in radians, you've got to make sure you're in radian mode. So we'll finish with this example. This is a second degree equation. It's already in terms of one variable, the tangent of x. If it helps you, then let y be equal to the tangent of x. And now I'm solving y squared minus y minus 2 is equal to 0. That's a relatively simple thing to factor. Y and 1 and 2. 2's negative, 1's positive. Set each factor equal to 0. You get y equals negative 1 and y equals 2. Now tangent can actually be greater than 1, so I'm not going to cross that out. I end up with the tangent being tangent of x is equal to negative 1, and tangent of x is equal to 2. In this case, this happens to be a special angle. That's negative pi over 4. But this one, you would use the inverse tangent to get an answer. And if you want, in this case, it ends up being about 1.107, because the tangent is positive in the first quadrant, and this is that's why you would just have this one answer. So sometimes you have to use the inverse function to solve these. And in class, we're going to solve more of these. We're going to practice more and also look at how to use your calculator to check your work.